A dead star just released more energy in a fraction of a second than our sun produces in 10,000 years, and the only thing that moved was its surface. A neutron star is what remains when a massive star exhausts its fuel and collapses. The collapse is not gradual. A core roughly the size of a city compresses under gravity so intense that protons and electrons are forced together, producing a sphere of almost pure neutrons packed to a density that exceeds anything achievable in a laboratory. 1 teaspoon of this material, removed from context, would weigh approximately 1 billion tons. The outer layer of this object forms a crust, a rigid crystalline lattice of atomic nuclei embedded in a sea of free electrons. Deeper layers transition into more exotic states, but the crust behaves in broad terms like an extraordinarily dense solid. It holds its shape. Under normal conditions, it accumulates strain slowly, over thousands or millions of years, before eventually releasing that strain in what can be described as a structural adjustment, a crack, a shift, an event that should be, by any reasonable physical estimate, a minor release of localized stress energy. That is not what is observed. When the crust of a neutron star fractures, the energy output recorded at detectors can reach levels that dwarf the total electromagnetic output of the sun by factors that are not small. The 2004 detection from SGR 1806-20 registered a gamma-ray burst so intense that it measurably ionized the upper atmosphere of Earth from a source located approximately 50,000 light-years away. The burst lasted less than a second. The energy released in that fraction of a second approached 10 to the power of 46 joules. The crust moved. The energy release was incompatible with the crust having moved. A dead star cracked, and the crack had the energetic signature of a planetary-scale catastrophe. The standard framework for understanding how strain accumulates in a neutron star crust is derived from solid-state physics scaled to extreme density and magnetic field conditions. The crust is not a simple material. It exists under pressures and magnetic fields that have no laboratory equivalent, but the underlying physics of crystalline stress and fracture is well characterized. Strain builds. At some threshold, the lattice breaks along a fault line. Energy releases. The crack propagates until the stress is distributed. Under this framework, the energy available for release is bounded by the elastic energy stored in the crust. Estimates of that stored energy, even accounting for the extreme conditions inside a neutron star crust, fall significantly short of explaining the largest observed events. The gap is not marginal. In extreme cases, the observed energy exceeds what crustal elastic energy alone could plausibly provide by several orders of magnitude. Something else is contributing. The question is what? The first serious candidate is the magnetic field. Neutron stars with the strongest observed fields, called magnetars, carry magnetic fields reaching 10 to the power of 15 Gauss, roughly a quadrillion times stronger than Earth's magnetic field, and trillions of times stronger than the strongest sustained fields humans have produced in laboratory settings. A field of this intensity is not a passive feature of the star. It stresses the crust. It deforms the lattice. And when the crust fractures, the magnetic field lines connected to it are forced to reconfigure. Magnetic field reconfiguration on a neutron star is not a smooth process. The field lines threaded through the highly conductive interior resist sudden change. When a fracture forces reconfiguration, the result may be a violent release of magnetic energy, similar in concept to the magnetic reconnection events that drive solar flares, but occurring in an environment where the magnetic energy density exceeds anything in the solar context by many orders of magnitude. Under this explanation, the crust fracture is not the energy source. The crust fracture is the trigger. The magnetic field is the reservoir. This explanation has real predictive force. It connects the most energetic observed events to the objects with the strongest measured fields. Magnetars, the subset of neutron stars with extreme magnetic fields, are the sources of the most powerful observed starquakes. The correlation holds across multiple detected events. If the magnetic field is the energy reservoir, the scaling of event energy with field strength is at least qualitatively consistent. The issue is that magnetic energy release in this context is not fully modeled. The physics of how magnetic energy couples to crustal fracture, propagates outward, and converts into the observed gamma-ray emission involves a sequence of steps that are individually uncertain. Current models of this process require assumptions about the internal magnetic field geometry, the depth and extent of the fracture, and the conductivity structure of the crust that cannot be directly confirmed from external observations. The model fits available data, but it does so with enough free parameters that fitting is not the same as understanding. More precisely, no predictive model currently exists that can take the initial conditions of a magnetar and calculate in advance the energy of its next major outburst. The second candidate shifts attention inward. Below the crystalline crust, neutron star interiors are predicted to contain states of matter that do not exist naturally anywhere else in the universe. At sufficient depth, neutrons may form a superfluid, a quantum state in which matter flows without friction, governed by quantum mechanical rules rather than classical hydrodynamics. Deeper still, current models predict increasingly exotic phases, nuclear pasta, where nuclei deform into sheets and tubes under extreme pressure, possibly quark matter, where individual nucleons dissolve and their constituent quarks become the relevant degrees of freedom. A fracture in the crust does not occur in isolation from what lies beneath it. The crust sits on top of this layered interior, and the two are coupled. When the crust cracks, stress waves propagate downward into the superfluid layers. In a classical solid, those waves would dissipate. In a superfluid, the coupling between the crust and the interior is more complex. The superfluid responds to changes in rotation and stress in ways that can involve sudden transfers of angular momentum back to the crust, a process called a glitch when observed in pulsars. Some researchers have proposed that the most energetic starquake events involve not just the crust fracturing, but a coupled response from the superfluid interior that amplifies the energy release far beyond what the crust alone could produce. The superfluid becomes a second reservoir, triggered by the fracture and releasing energy through quantum mechanical vortex dynamics rather than through classical mechanical processes. No direct observational evidence currently allows us to confirm what state the interior of a neutron star is actually in at any given depth. Every model of the interior is constrained by external measurements, rotation rate, cooling curves, glitch statistics, and those constraints still permit a range of interior configurations. The superfluid amplification model is consistent with available data. So are models that do not require it. Two competing explanations, neither closed. What makes the paradox structurally stable, meaning what prevents either explanation from simply winning, is the same thing that prevents either from being discarded. Direct measurement of the neutron star interior is not possible. The relevant physics occurs behind the stellar surface. Gravitational waves from these events have not yet been detected with sufficient resolution to map internal dynamics. The observable outputs, gamma-ray flux, duration, afterglow decay, constrain models but do not uniquely determine them. The crust fracture is confirmed. The energy output is confirmed. The mechanism connecting them remains contested. What cannot be modeled cleanly is the interior coupling. Neutron star matter at the relevant densities has no experimental analog. The equations of state used to describe it are extrapolations of nuclear physics into a regime where nuclear physics has never been tested directly. Different equations of state, different assumptions about how matter behaves at these densities, produce different predictions for interior structure, superfluid coupling, and energy transfer efficiency. Available observations cannot yet distinguish between them at the level of precision required. The magnetic field models have the same problem in a different form. The internal magnetic field geometry is not observable. Only the external dipole component can be measured with confidence. Interior field configurations that would substantially alter the energy available for reconnection are plausible but unconfirmed. Any model that invokes the internal field as a primary energy source is partially built on parameters that remain unobserved. There is a specific measurement that would help resolve this. If gravitational waves produced during a major starquake were detected with sufficient signal-to-noise ratio, the oscillation modes encoded in those waves would carry information about the stellar interior, about crust thickness, about coupling to the fluid layers, about internal density profiles. The event in 2004 may have produced detectable gravitational waves, but no gravitational wave detectors of sufficient sensitivity were operational at the time. The current generation of detectors, LIGO and Virgo, have sensitivity ranges and target configurations optimized for binary mergers, not for the specific frequency range expected from neutron star crust oscillations. Detection remains possible. It has not yet occurred. The starquake of 2004 also revealed something that was not anticipated. In the minutes following the initial burst, the source continued emitting quasi-periodic oscillations, repeating pulses at specific frequencies that lasted far longer than the initial event. These oscillations are believed to encode the vibration modes of the star as a whole, driven by the fracture event. The frequencies measured correspond to predictions made by models of neutron star oscillation, providing some confirmation that the global structure of the star was involved in the event, not just a localized surface fracture. The quasi-periodic oscillations also provide a potential window into interior physics through their frequency spectrum. Early analyses suggested partial agreement with theoretical predictions. Later analyses, using improved methodology, found that the agreement was less clean than initially reported, and that some observed frequencies do not match any standard oscillation mode predicted by available models. The crust fractured. The star rang. Some of the notes it produced have no explanation. What began as a question about why a crack in a stellar surface produced too much energy has expanded. The energy surplus implies either that the magnetic field is acting as a reservoir in ways not fully modeled, or that the interior is coupling to the fracture in ways not fully understood, or both, or something else not yet identified. The oscillation frequencies suggest that the event involved the whole star in a way that current models of neutron star structure do not fully account for. The gap between the observed behavior and the available theoretical framework is not shrinking under closer examination. The most energetic starquake ever recorded released enough energy to have been detected from 50,000 light-years away. The object that produced it has a surface area smaller than a city. The fraction of that surface that fractured may have been a few kilometers across. The energy budget has no confirmed source. The oscillation spectrum has no complete interpretation. And somewhere in the galaxy, magnetars are accumulating strain right now, in interiors no model has fully described, approaching thresholds no equation can currently predict.